Ready? Live? Okay. So hello and welcome to BYJU'S, or I should call it as Aakash plus BYJU'S JEE channel. We are here for Mission JEE 2022. As you know, this is a wonderful session that we have started off for our wonderful students like you to learn, to understand, and then to solve questions. Well, what is the agenda for today's session? In today's session, we are going to see concepts of photoelectric effect, matter and waves, or in other words, the dual nature of matter and radiation. Okay? So yes, we'll just go through the basic theory and I'll give you an idea about how do you solve questions, how do you approach the questions, and also if something appears to be very lengthy at the outset, how do you take care of those things as well. So if you guys have joined me, can you just give me a hi, hello, so that I know that my audio, video, everything is clear, and then we can start off with the session. So guys, just put your responses in the chat, and then we are going to start off with the session of JEE Mission 2022, Photoelectric Effect and Matter and Waves. So yes, we have people joining in. Anand, hello. And A2 Clips, you have weird channel names. Okay, so Viplav, Sankalp, good evening. Good evening, nice to see you. Pintu said, I'm not understanding chemistry. Well, Pintu, don't worry, this is a physics class. Okay, I got it, Pintu, don't worry. Okay, this is a physics class, so I hope you understand physics at least. Sandeep, Captain Jack Sparrow, welcome. You are a regular visitor to our channel. So, well, we are going to have a fun session, a learning session. Let's get started, shall we? Just give me a thumbs up if my audio and video, everything is clear to you. And then we'll start with the session. Hello Shubham, Anmol, hello, good evening. Okay, if we are good to go, if my voice is clear, if my audio is clear, let's get started. Okay, so you know that there was a big tussle between understanding of the nature of the light. Because when we started out with the nature of the light, the first theory that we got was from Sir Isaac Newton. And he told that light is a particle. But when light is a particle, it has to, it has to prove by certain experiments that the behavior of light has to be like a particle also. Well, we believed Sir Isaac Newton for about 100 years because he predicted that light is a particle, or he gave a theory that light is a particle in around late 1600s. For around 100 years, we followed and we thought that yes, we have cracked the code of understanding light. And then what happened is that there were scientists who were doing experiments and they found out that the behavior of light resembles more towards that of a wave, because that's how the energy transfer is taking place. And we had certain experiments which proved that light undergoes diffraction, light undergoes superposition, it follows superposition principle. And then we thought, okay, fine, now we have solved this mystery of light. Well, to our surprise, in early 1900s, Heinrich Hertz actually did an experiment, and he found out that when certain radiations of light are hitting a surface of the metal, then electrons were ejected, correct? Now you might say, sir, what's special about that? Yeah, light has energy, we know it, it hits and then the electrons are ejected. The problem, however, was that if a light, imagine this is an electron, and if a radiation of light is hitting this, an electron gets ejected. Let's talk about the velocity of electron, which means I'm talking about the kinetic energy of electron. So one is the kinetic energy of electron. Okay, what will be the kinetic energy of electron? And second is, what about the intensity of the light? Because we thought that light is a wave, and the more intense it is, it should have more energy associated with it, of course. So second thing was about intensity. What happens to intensity? Now what was found out is that if you believe the wave theory is correct, then the more intense the light is, more electron should be coming out. Correct? Or electron should be coming out with higher value of energy, rather I should say that. What was found out is that the condition was on frequency. So you required a particular type of frequency, a particular value of the frequency, a minimum value of the frequency, and this is what we call as threshold frequency. Okay? Sujal is asking, sir, is it applicable for NEET? Absolutely it is applicable for NEET, Sujal, because this topic is there in your NEET and a very important one as well. And to also give you a context about this topic, well, this is a topic from the chunk which is called as the modern physics. And even if you look at the past 5 years paper, only in JEE Mains exam, at least 5 questions have been asked, okay? And there were few of them from this topic only. So you need to understand that what topic we are going to go through. Now, so what happened? The whole scientific community was confused, as in that, what is light again? The same old question, 200-year-old question, that what is light, again came back haunting the physicist. Then came Albert Einstein, and he gave a theory, and he told that, okay, light is made up of packets of energy, and we call these packets of energy as photons, and their behavior will be like particle. All right, so just imagine that we were thinking that light is a wave. Like, just imagine it like a river in which the water is flowing, right? So it's like a wave. But then came another idea, a breakthrough, wherein Einstein told, no, that's not the case. It's like the bottles of water, something like this. And when you throw it from one point to another point, they travel as a particle. But inside, what is there? A wave. But we are not here to discuss about what's inside this. What we call this as the particle of light, we call that as photon. Okay? So light is not a wave but a particle, and was proved by the black body radiation. Okay? Light is made up of packets of energy called photons, found in the form of chunks of energy. So now we started believing, okay, fine, now that light is a wave. But again, there were certain fundamental nature of light that we were not able to explain with the help of this particle theory as well. Okay, right? So what happened? We told, okay, light is going to have a dual nature. Cool? Light is going to have a dual nature. Now you might think that that's just a scientific gimmick where we are trying to, just adjust the bits and pieces, and we are trying to figure out something. So how can it be both? I'll give you your example. Okay, let's say you play cricket, and probably you are a batsman. So when you are on the ground, you play cricket and you are batting, how well you bat or your batsmanship is actually what is being seen over there on the cricket pitch. But the same guy comes back and attends a physics class. Now then, he is a physics student. So how good he is will be evaluated on the basis of how much physics he knows. Which means it's the same person who is having this dual nature, one of that of a sports person, another one as that of a student, of that of a person who wants to pursue physics. So it's the same person, but it shows dual nature. Correct? We all take up dual, triple, multiple natures. You are somebody's son, somebody's brother, correct? Or somebody's daughter, somebody's sister, like that. We all take up different roles. So for that particular requirement, whichever nature suits us in explaining things, we take up that particular nature. But it was also established that yes, there is limitation to the wave theory, which we have thought that wave theory is going to be an absolute theory, and we have cracked the code of understanding of light. So now, this chunk that we are going to deal in today will consider light to be made up of these photons, all right? And that is why the dual nature of radiation which is a wave or light that we were talking about, and matter. So later on we'll also understand that matter, just for example like an electron, also behaves as a wave. Correct? So that's kind of weird, but that's how it is. So let's start off with understanding and getting little bit insight into this thing which we are calling it as photon. All right. So the minimum energy of a photon is given by E is equal to h nu, and as you can see, the energy of a photon is dependent on the frequency. Okay, if you think about light, what it can have? It can have actually two things. One is the intensity, which means how bright it is. Another one is the color, correct? So you change the frequency, what you have changed is also the wavelength, so you have changed the color. If you change the intensity, what you have made it? You have made it dimmer or you have made it brighter. Got it? Okay. So you see, the energy of this photon actually depends upon the frequency, contrary to the idea that we had that in case of waves, intensity is how we think of the energy associated with a wave, isn't it? So when we talk about a photon, its energy will be given by E is equal to h nu, and energy is quantized, so you cannot have half of a photon. You cannot have 1.5 of a photon. Either it will be 1 photon or 2 photon or 3 photon and like that. All right. Okay. So you have to think now, you have to redefine your imagination, and you need to think in this sense that whenever I say the light is incident, you need to imagine that there are certain photons which are incident over there. Got it? Okay. Cool. So what was proved about the nature of the light? Proved the dual nature of the light, that is wave nature and particle nature. This proved that light consists of particles associated with a definite amount of energy and momentum. These particles were named as photons. The momentum of a photon is defined by P is equal to h by lambda, and the energy of the photon is given by E is equal to hc by lambda, where h is the Planck's constant, c is the speed of light. And all these photons travel in vacuum with the same speed, or in air with the same speed, that is with a speed of 3 into 10 to the power 8 meters per second. Got it? Okay. Now let's get into this experiment exclusively. Let's see a setup and what was happening over there. And I expect you guys to know bits and pieces of this part as well, because you must have studied it somewhere, probably in your school or in your tuitions or from somewhere, from your friends. Okay. So yes, photoelectric effect is not something which is absolutely new to you. So given that you understand the basics, let's look at the setup. The setup consisted of a vacuum tube wherein we had one end as C, another end as A. Okay. And what used to happen is we'll have this transparent tube from where light is going to be incident over here. As the photons come, they'll strike this metal surface and electrons will be ejected. Okay. Now even if the cell is not there and you have the circuit as a complete circuit like this, even if the cell is not there and I just complete the circuit like this, imagine that this is not there initially, still you're going to see if the light is greater than or equal to a desired frequency, which we are calling it as the threshold frequency, you're going to see electrons come over here and you're going to see the current in the circuit. Now these current which is present because of the presence of the photons are called as photocurrent. So they have a special name. It's called as what? Photocurrent. Now what's the use of this battery and all that? You'll come to know. Good? No problem. Okay, Captain Jack Sparrow is saying please make a video on wave optics also. Definitely we'll do that. Okay. Yes, your feedback is taken. We'll definitely do that very soon. No problem. Manav, no problem. It's totally fine, Manav. You're not that late. We just got started. So yes, I was talking about this setup. Now what happens once the light is incident and it is beyond a particular frequency, which we are calling it as threshold frequency, which we are taking it as that it is more than that frequency, then what will happen? Now the light is incident and you can see the electrons popping out, right? You make it more intense. You make it more intense and you see the higher value of the photocurrent. So you are also plotting the graph of photocurrent versus intensity. Now, what is the meaning of this? What does this tell you actually? It tells you that on increasing the intensity, the number of photons have increased. And now let's suppose that if every photon takes out or kicks off one electron. Now initially if you are using, let's say, 10-watt bulb, just an example, okay. Now it is in the zone wherein photoelectric effect is happening. there can be a case wherein you give any amount of intensity, and if the frequency is not sufficient enough, then you won't get any photoelectric effect. There has to be a bar on the frequency, and this frequency is called as the threshold frequency. Okay, now you see what happens over here. It means that once you have increased the intensity, and this is the most important line of this entire topic. So what does this intensity tell you? Intensity means that the number of photons have increased, and if the number of photons have increased, they are going to knock off more number of electrons, right? So if a 10-watt bulb is taking off, let's say 10 electrons, just an example, okay, then a 100-watt is going to be 100 electrons. So more electrons will start flowing, correct? Yeah, Pinky Kumari has a doubt. I'll just go through your doubt. Sir, here frequency of radiation must be greater than the threshold frequency, then only photocurrent will be directly proportional to the intensity. Absolutely correct. Yes, yes. Only and only when this frequency is greater than the threshold frequency. If it is less than the threshold frequency, no amount of intensity is going to take the electrons out, because the energy of the photon is dependent on its frequency. So you are absolutely right, Pinky. Good, well done. Okay, so in this example we have taken a scenario wherein it's already more than the threshold frequency, so photoelectric effect is happening in this case. Now what will happen? As you make it more and more intense, more and more current will start to flow, which means photocurrent, once the photoelectric effect started, will be directly proportional to the intensity of light. Got it? Okay. Now you see, as all these electrons will start coming out, what will happen? They'll start clubbing up over here, correct? And in this region, what will get developed is the space charge. So in that zone, there will be a negative charge, a net negative charge. Can I say over here? Understand, why did we place a cell over here? Why did I place a cell? Why did I place a battery over here? Okay, in this setup. So you need to understand the setup first, then things are going to be very easy. Okay, don't worry Girija, we are just getting started, so there is no need to be sorry for being late. I appreciate your presence. Just be here, try understanding everything. I'm going to teach you in and out, and we are also going to solve some wonderful problems. So this concept, as you know, this topic itself is conceptual in nature. So you need to have a notebook, and you need to take down the running notes, okay, attended as if you are sitting inside a class. So you see, once you look at this zone, okay, Atul is saying photoelectric effect, please teach again. We are going through photoelectric effect, Atul, don't worry. I'll repeat what I have just now told you, okay, in a nutshell I'll tell you, don't worry, okay. So what I'm saying is, the moment now this radiation is hitting and electrons are getting ejected, okay. Now there is a kind of a traffic jam of electrons, okay, because a lot of electrons have got accumulated over here, which means in this space, the net charge has become negative, correct? So there is a net negative charge. Now imagine the next electron which is going to come outside, it's going to experience a force in opposite direction, right? It's going to experience a repulsion. Why? Because there is a space charge which is present, which is negative, correct? Because of all these accumulation, okay? Yes, Prajapati, yes, go ahead, please ask your doubt, okay? So now as this electron comes in, it experiences this repulsion and it is not able to come. So which means that you are going to see the graph declining probably after a particular amount of time, right? You want to see a proper flow of the electrons so that you can sustain this current. To do that, what you do is, you start increasing the potential. And what kind of potential? Positive potential over here. The moment you start increasing the positive potential, what will happen? All these electrons will start getting accelerated. All these electrons will start getting accelerated in this direction, and this entire jam that we had, the traffic jam that we have, will get accelerated towards this A. Got it? Yes? Okay. Now what will happen? There will be a smoothness of current. But can we just keep on doing that? Can we just keep on increasing the potential and more electrons will start coming? Now, you need to understand one very important thing, that this potential is not producing any electrons. The electrons are being produced by this radiation. So if you have fixed onto an intensity, and let us say now it's 100-watt bulb that you are using, and now for 100 watt each wattage I am assuming that you can take out 1 electron, so it's going to give you maximum 100 electrons. So once all this 100 electrons are flowing in the circuit, then you reach to a stage which we call as the saturation stage, where the maximum amount of current that can flow, it can flow. All right, so the maximum amount of current that can flow is flowing now in the circuit. So you can see the maximum, I go on increasing the voltage, but after a certain time I see that it reaches to a saturation state. It reaches to a saturation state. Okay, now you see what happens. So what we do, we now interchange the potential, which means I make A negative with respect to C. Now what will happen? All these electrons which were coming like this, and they had some energy. And what kind of energy? Kinetic energy. So these electrons are possessing what? Kinetic energy. So as these electrons starts moving and they possess kinetic energy, and you put a negative potential, now what will happen? These electrons are going to experience a force. In which direction? In opposite direction. But since they have energy, they will keep on reaching. You go on increasing this negative potential, you keep on increasing this negative potential. What will happen? They will suffer a repulsion, but since if they are energetic enough, they will keep on reaching this point A. So if the electrons keep on reaching from C to A, the current will flow. But now the number of electrons which have started from C and they are reaching to A have declined, which means the current will also go down. Okay, so the current is also going to go down. There comes a point where even the maximum energetic electron, the electron possessing maximum kinetic energy, also cannot reach to this point. At that point, what will happen? The current is going to stop. The current is going to stop, and that potential at which the current stops is called as the stopping potential. That potential over here, the potential of A with respect to C, okay, if it becomes sufficient enough so that even the highest energy electrons are not able to reach from C to A, that potential we call it as the stopping potential. So you go on increasing this, and you can see what happens. The electrons start suffering a repulsion, and I want to show you one more time with the animation that what happened. Okay, now you see, you change the terminal, and what we have done is as the electron starts coming, they suffer repulsion, and there comes a point where even the maximum energy electrons, okay, are not able to reach to point A, and at that point the current stops, and we call this as stopping potential. Cool, stopping potential. So as you can see, we apply this negative potential, and there comes a point where you have this stopping potential. Okay, now let's look at certain important points. So saturation current increases with increase in intensity. Number of photoelectrons emitted is directly proportional to intensity, and at a given frequency of incident radiation, the stopping potential is independent of its intensity. Why? Because you see, the electrons which are moving, they possess kinetic energy, and when they are stopping, when they're stopped by this negative potential, this kinetic energy gets converted to their potential energy. Got it? This kinetic energy will get converted to the potential energy. All right. So potential, this stopping potential is sufficient to stop the most energetic photoelectron. So at that point, what I can say? So these electrons which were having maximum energy, they also cannot reach to this point A, which means, can I say the maximum kinetic energy will be equal to the stopping potential, which will be E times of V? Yes. Is equal to what? Is equal to E times of V. Got it? Okay. So why only some metals are photosensitive? Well, the nature of photosensitivity, it comes from the lattice structure and also based on the electronic configuration. All right, okay, but we are not going into that part now. Just try understanding this. Okay, so all the materials that we'll be using only photosensitive materials, and we are talking about the surface of a metal. Now, a surface of a metal is going to have all these free electrons, and these free electrons have an ability to move out, but they're not going to move out just like that. They need some energy from outside. And who is going to provide that energy? Well, we provide that in form of radiation from light. We provide that from photons. Okay, so what do you get now? K max is equal to EV naught. Now, you recall the Einstein's photoelectric effect equation. What did he tell? He told that the maximum kinetic energy is going to be equal to total energy incident minus phi, where phi was the work function. Phi was the minimum energy required to remove an electron from the surface of a metal. Correct? Okay. So, what we can write? Kinetic energy maximum can be written as EV naught. This E can be written as H nu. I can write this as H nu. And we know that this phi is nothing but work function, which depends upon temperature and the nature of the material. So what I have for V naught or stopping potential, I have a new formula, H nu by E minus phi by E. Now when you look at this formula, you can actually see that this V naught depends only on this frequency and what? And the work function. Got it? So stopping potential has nothing to do with intensity. As contradictory to what we used to think in terms of what? In terms of what? In terms of waves. Correct? So it has nothing to do. Got it? Okay? Fine. So what equation did we get? This equation. A very important equation indeed. So you should star mark this equation. Cool? Okay. Now you can also write the same formula in form of Hc by lambda, and you can also plot a graph. You can go ahead and plot a graph. Okay. Yes, all these concepts were in class 11th, chapter 2 of chemistry. Some of it, yes, I totally agree. So the effect of frequency on stopping potential. So you know that if you increase the frequency, and if the threshold frequency is, the requirement of the threshold frequency is also higher, the stopping potential will also be higher. Correct? So you require then more energy to take electrons out of these metal surface. Okay? So for a particular metal, if the threshold frequency is higher, the energy requirement will also be higher, because the remnant is what you are getting in form of kinetic energy. And remember, the formula is only for KE max. Maximum kinetic energy, because the electrons are also going to lose and use some of its energy. As they come out, they'll be using some energy and they will be losing it in form of collisions and all. So you get all different values of energy of these electrons as they come out. But the formula only reflects the maximum kinetic energy, so do not make a mistake of writing it as kinetic energy. The formula is KE max, maximum kinetic energy. All right. The formula is of maximum kinetic energy is equal to the energy incident minus work function. So this is the actual formula. Okay. If you rearrange this and try writing it that total energy incident is equal to somehow has been used in kinetic energy plus work function. Well, this is wrong. This is a wrong approach. Do not fall for this trap. The formula is valid only and only for maximum kinetic energy. So you are going to get all these electrons which are having all these different values of energy, but this formula specifically is valid only for the maximum kinetic energy. And when it will have maximum kinetic energy, when it is going to possess the maximum value of kinetic energy, when nothing is wasted. Correct? When nothing is wasted, as simple as that. Okay. Next, let's talk about the saturation current. The saturation current is same for all frequencies. Stopping potential is higher in magnitude for higher frequencies. Obviously, because the moment you have told that the stopping potential is higher its energy requirement has to be higher, of course. Now if you plot a graph, you know that you are going to get a graph of a straight line with a negative intercept, correct? But with a positive slope. So if you have got two metals, metal A and metal B, and you need to talk about the stopping potential, okay? When you look at this graph, you see the stopping potential depends upon this threshold frequency. As we can see, for metal B, the threshold frequency is greater. And as you can see, for metal A, the threshold frequency is lesser. So if you have an identical radiation which is greater than the threshold frequency, but in both the cases, you see, more is this, more will be the stopping potential. Got it? More is this, more will be the stopping potential. Cool? Okay. So now when you actually plot a graph, this is how the graph is going to look like. So stopping potential varies linearly with frequency for a given photosensitive material. It varies linearly for a given photosensitive material. Cool? Okay. So now you have got all these graphs and you need to take care of all of these graphs together. Got it? So when you're looking at these graphs, there can be questions which are totally graph oriented, and we are going to see some questions like that as well. So you need to remember these graphs. Okay, it's not difficult to remember them, but you know, if you draw it a couple of times, you'll definitely be able to recall all of this. So well, if everything is set, shall we look at one simple problem? Yes? All right. Let's look at this question, and I hope you guys start answering the question. The question says, ultraviolet light of wavelength 280 nanometer is used in an experiment on photoelectric effect with lithium. Okay, the value of this threshold frequency, that is phi, is given to us, which is 2.5 electron volt of cathode. Find the maximum kinetic energy of the photoelectrons and the stopping potential. So come on, I'm going to give you 30 seconds and then I'll start solving this question. Read out the question. You have ultraviolet light of wavelength this much, and it is used in experiment on photoelectric effect with lithium, and phi is equal to 2.5 electron volt. Think and do it. What is the formula of maximum kinetic energy? What is the formula of maximum kinetic energy? You have the value of wavelength, you have the value of lambda. So you know the value of E, which is equal to hc by lambda. A shortcut formula would be, whenever lambda is given in nanometers, always use this shortcut formula. You can directly write in terms of electron volts. If you want to write the energy of a photon, you can use this shortcut. It will be equal to 1242 divided by lambda in terms of electron volts. Got it? Okay. So now you know the value of lambda, substitute the value of lambda and get energy in electron volt. Then it all comes down to this expression of photoelectric effect, which is K max is equal to E minus phi. Okay, K max is equal to E minus phi. Phi is already given to us, which is equal to 2.5 electron volts. Correct. All you have to do is substitute for phi, substitute for E, correct, and then get the value of maximum kinetic energy. Got it? The first one is fine. First part is fine. The maximum kinetic energy of photoelectrons is going to be equal to. So we find the value of E first, we substitute it, and then we get the value of Ke max. Next, stopping potential. As we know, E V0 is equal to Ke max, which means if I want to know the value of stopping potential, VO is going to be equal to what? Ke max by E. Correct. Okay, you substitute the value of lambda. What do you get? This is going to give you 4.4 electron volts, I think. So 4.4 minus 2.5, this will give you maximum kinetic energy will be equal to how much? I think it is going to be equal to 1.9 electron volts. And then what will be the value of V naught? 1.9 electron volt divided by E, so E gets cancelled and you get what? 1.9 volts. That's it. Easy. Easy, yes. Okay. Cool. So this is how you go about it. Kinetic energy maximum hc by lambda minus 5. We have the value of lambda. From there we can directly get all of this, and then we substitute the values. We get the value of Ke max and we get the value of stopping potential. All right. Yes. Shall we go ahead to the next question? Well, the next question that we have, it says a monochromatic light of wavelength lambda is incident on an isolated metallic sphere of radius a. The threshold wavelength is lambda naught, which is larger than lambda. The threshold wavelength is lambda naught, which is larger than lambda. Find the number of photoelectrons. So first question is, will photoelectric effect happen or will it not happen? Will it happen or will it not happen? First you have to answer that. What we have told, that if the frequency is greater than the threshold frequency, correct? If the frequency is greater than threshold frequency, then only we are going to get the photoelectric effect. Similarly, if the wavelength, if the threshold wavelength is lambda naught, has to be larger than the incident wave, correct? Okay, so find the number of photoelectrons emitted before the emission of photoelectrons is going to stop. Think. What we can write? How do we write? How do we solve this question? Again, very simple. Again, we'll start off with the same basic idea. Same basic idea. What was the basic idea? The basic idea was Ke max is equal to hc by lambda minus 5. Cool. Okay. Now, hc by lambda minus 5. Can I write this phi as? Can I write phi as hc by lambda naught? Yes. That means I'll get kinetic energy max is going to be equal to hc 1 by lambda minus 1 by lambda naught. Okay. Okay, is this okay? And this will be equal to what? Terms of EV. Now what about this potential? What about this potential? This V can be written as KQ by R. In this case, we know potential, right? So K is 1 by 4 pi epsilon naught. Q, let's say there are n number of photoelectrons, so n times of E divided by R, which is A. Okay. We take this and we substitute it over here instead of V. What do we get? HC 1 by lambda minus 1 by lambda naught is going to be equal to 1 by 4 pi epsilon naught n E square by A. Now from here you just need to get the expression of n. That's it. Okay. All you have to make n the subject and get the expression. That's it. This is what you are supposed to do. Okay. Why all the energy is written in form of electron volts? Why not in joules? Well, you can always convert electron volts to joules. All right, but over here, see, joules generally we go with when we are dealing with heat or when we are talking about mechanical work. When we talk about energy in electrical sense, well, it's always better to talk in terms of electron volts. Okay, fine. I hope I answered your query. Cool. Okay, so you see what goes on in this question. All we have to do is solve it and then substitute the final result. Get the expression of capital N. No problem. One more question. Now this is a question which seems slightly difficult at the outset. It is not. Why it is not, I'll tell you. Because when you look at this question, just by basic understanding, probably you will be able to understand that how to go ahead, how to go forward with this question. The question says the graph is showing variation between stopping potential V0 with frequency F. For two photosensitive metal plates P and Q, okay, Option A says explain which metal has smaller threshold wavelength. And option B says explain with reason which metal emits photoelectrons having smaller kinetic energy for the same wavelength. Look at the graph. Identify. It's a graph between VO and frequency. What you can identify from here? Write the expression of VO. Start off with writing the expression of VO. And then we are going to go ahead. Okay? So yes, I'll just wait for your answer. Let's see if you are able to do it or not. How we should start? VO will be equal to h nu by E minus phi by E. This is the expression that we have learned. Correct? Okay. Now just look at these 2 points. These 2 points. When you look at these 2 points, what do you observe? You observe that the value of the frequency is higher over here. The value of the frequency for Q is greater. So I can write VQ is greater than, and this is nothing but stopping potential. So VO of Q is greater than VO of or stopping potential of P, which means that you require a larger amount of energy to take the electrons out from metal surface, which one? Q, right? The requirement is that to stop those electrons also, you require a larger amount of energy. You require a larger amount of energy to stop the electrons because the stopping potential is higher, right? Okay. Now, if the stopping potential is higher, it also means that the total energy that you are giving and the kinetic energy that you are getting, what will be the relation? So I'm just giving you some hints, okay? Just think about these hints and try solving it. Just try solving it. How do we do this? We have VO is equal to h nu by E minus phi by E. We know the expression of kinetic energy also. Ke max is equal to hc by lambda minus phi. Now you know that stopping potential of P is less than stopping potential of Q, correct? Or stopping potential, or the, which means that the value of phi will be greater for Q, correct? That means that lambda for P, lambda naught for P has to be greater than lambda naught for Q. Once you know the expression of frequency, you also know the expression or the relation of lambda, correct? And the same thing about the kinetic energy. The same thing with regard to the kinetic energy. So this is what you get. Simply put, this is what you get. Okay? The next question, the third part of this question is that if the distance between the light sources and the metal P is doubled, how will the stopping potential change? If you increase or decrease the distance, does it affect the stopping potential? Well, stopping potential, as far as we know, only depends upon what? Frequency. So once stopping potential depends upon frequency, what happens? It has nothing to do whether you double it, triple it. Correct? Okay, easy? Easy, right? So there will be no change. There will be no change. So no change, good. Now, let me give you an MCQ. Let's solve one MCQ together. So we have a question. The question says, in a historical experiment to determine the Planck's constant, a metal surface was irradiated with light of different wavelengths. The emitted photoelectron energies were measured by applying a stopping potential. The relevant data of wavelength lambda of the incident light and the corresponding stopping potential are given below. Okay, they are given below. Will the intensity change in case 3? So Pinky, we are not talking about intensity over here. So nothing has been given in the question. So we'll assume that the intensity remains constant until and unless it's mentioned. We'll say that it's going to remain constant in the previous question. I hope you got the answer for this, right? Now let's try this one. we need to calculate the Planck's constant from such experiment. What you have, I can say this is lambda 1, stopping potential is VO, let's call it as VO1, this is lambda 2, this is VO2. Okay, again going back to the same basic equation, that is KE max is equal to what? It's equal to E minus phi. Think KE max can be written in terms of stopping potential. We have this one formula. What are the values that are given to you, and you have got 4 options. Think and do it. Think and then attempt. You need to find the Planck's constant. You have these values. How do we go about it? We know the formula KE max is also equal to EVO. So can I write EVO is equal to HC by lambda minus phi? It's the same metal, right? So I can write this, I can write it for 2 different sets. Let's call this as lambda 1, let's call this as lambda 2. Let's call this as VO1 and let's call this as VO2. What will be my first equation? First equation for this one. Okay, I can write EVO1, okay, EVO1 is equal to HC by lambda 1 minus phi. This is our equation number 1. Equation number 2 will be EVO2 is equal to HC by lambda 2 minus phi. Okay. Now find the difference, that is 1 minus 2, and all these small things mathematically you need to do. Okay, these mathematical things you have to do it. So find the difference, and that's all, because now you'll be eliminating once you have got the difference, that is once you find 1 minus 2, what you have got is you have eliminated this phi, which is not required, correct? So what do you get? EVO1 minus EVO2 is equal to HC by 1 by lambda 1 minus 1 by lambda 2. Now in this equation, you know everything. You know the value of E, you know the value of V1 and V2, or VO1 and VO2, and you know the value of C, you know value of lambda 1 and lambda 2. So just substitute and get the value of H. So once you calculate that, and I'm sure that you'll be able to do this because everything is given more or less. So once you calculate that, what do you get is the value of H as 6.4 into 10 to the power of minus 34. Yes, and that makes which option as correct? That makes option B as the right choice. Okay. Now let's move ahead and let's talk about a problem. The problem where the wave theory failed to explain this photoelectric effect, and we want to understand that why did it fail? Why did the wave theory fail to explain this idea of photoelectric effect? Okay, so there was this intensity problem. So what happened? According to the wave theory, okay, yes, Somnath, you have answered it correctly. B, option B, that's right, option B is the correct one. So according to the wave theory, if I talk about the intensity, you know, is proportional to square of the amplitude. So if the intensity of the light falling on a metal is increased, then what should happen? The amplitude should increase, and if the amplitude should increase, the energy should increase. That technically meant that if I make the light more intense, so for example, if I am using a 5 watt bulb, I increase it to 100 watt bulb or even 1000 watt bulb. Correct? I should get more and more electrons, which was happening once the photoelectric effect started. But I'm talking about a threshold frequency wherein the light that you're using is less than the threshold frequency. Okay? So let us say that there is a particular metal plate, okay, and it requires some value of frequency nu, and this is nu naught, that is the threshold frequency for this one, and you are giving a frequency which is lesser than this frequency. but you keep on increasing the intensity. You keep on increasing the intensity. According to the wave theory, as the intensity increases, the energy should increase, the amplitude should increase, and you should get photoelectric effect. Okay? What happened? That it turned out this is not the case with light. We thought that we should get more and more kinetic energy of the electrons. That just did not happen. But we were using a very less intense light which is greater than this value. Even we used 5 watt, we were able to get the photoelectric effect. Okay, just give you an example. Imagine there is a small boat like this and there are waves which are coming. You make these waves intense. So what I did, I had this boat and I make this wave intense like this. What is going to do? It's going to disturb this, right? Because more the intensity, more the energy. This is what we think when we talk about waves, right? But what happened in case when we observed with experiments is that if you have the same boat and you want to tilt it aside and you start hitting this with small, ping pong balls, and you have taken probably 1000 of them, and then you want to knock this boat off, but that doesn't just happen. But if you have a boat like this and you have really one massive ball, all it takes is one massive ball, it goes and hits it, correct? So you tell me, is this experiment verifying a particle nature or a wave nature? This is what should have happened in case of wave. This is what was expected. But wave theory let us down in explaining this experiment. So all it requires is one single ball big enough to knock off this boat. And this is what we observed in experiment as well. The maximum kinetic energy of a photoelectron doesn't depend on the intensity of the incident light, which means something was wrong with this wave theory. Something was wrong with our understanding of this photoelectric effect and trying to figure out that what is going on with this wave theory. There was a second problem also, however. The second problem is that when all this light is incident, when all these frequencies are incident, irrespective of the frequency, we should get photoelectric effect. This is what is told by the wave theory, correct? The photoelectric effect should occur for any frequency of the light, provided that the light is intense enough to eject the photoelectrons. It's obvious because the wave theory tells us that the total energy, the energy associated with a wave, is associated with its intensity. So more intense you make, the more energy the wave carries, and if it goes and hits a particular surface of the metal, then electrons must be ejected. What we saw is that this is not happening experimentally. Right? So experimentally what we saw is that the photoelectrons will get ejected only when the incident light frequency is more than the threshold frequency, immaterial of whatever intensity you put. If it is less than the threshold frequency, you will never get photoelectric effect. Okay? Irrespective of whatever intensity you put, if the frequency of the light is less than the threshold frequency, then photoelectric effect is not going to happen. Okay, third problem was the time delay. What was there in the time delay? Now imagine a wave which is coming and is incident on the surface of the metal. As these wavelets come or the wavefronts come, energy will be distributed to these electrons on the surface, and it will take some time for these electrons to absorb this energy and to come out of the surface, which means there is going to be a time delay. So it will take some time for this incident radiations and these wavefronts to come and strike the metal surface, and all these electrons are going to get this energy. It will take for them these electrons are going to take up some time in absorbing this energy, and once they have got this energy, once this energy is sufficient enough, then only they can come out of this metal surface and photoelectric effect is going to happen. Again, what was seen is that it was instantaneous. The electrons will take some time to accumulate enough energy to escape from the metal surface. Hence, there should be a time lag. This is what was expected, that there has to be a time lag. Now, what we saw experimentally, however, was totally different. which means there was instantaneous emission. The moment you put a light of sufficient frequency on this metal surface, what did you see? You saw that there was instantaneous emission of electrons. So all these points made the wave theory failure to explain this phenomena of photoelectric effect, and that is why photoelectric effect is actually regarded as one of the most important experiments ever conducted, which gave us an idea about the light. So it failed on three aspects. Okay, what were those three aspects? Threshold frequency, maximum kinetic energy, and instantaneous emission. Now there are certain things that you can explain with the help of the particle nature. There are certain things which you can explain with the help of, okay, Jay Shah is asking, could you explain the frequency dependence? Okay, so you see, energy of a photon is given by h nu. Okay, so now if more is the frequency, more will be the energy. Correct. Now imagine this is a metal surface and some light is coming. Okay, let's say that it requires a frequency of, let's say, blue. Okay, and the light you are putting is red. Now if I compare the frequency of red and blue, you know that the frequency of blue is greater than frequency of red. Or you can also think in terms of what? You can also think in terms of the wavelength. Okay, you can also think in terms of the wavelength. So wavelength of red is more than the wavelength of blue, correct? Okay, because I can write this formula further as E is equal to hc by lambda. Now for red you use a 5 watt bulb or a 10 watt bulb or a 100 watt bulb or a 1000 watt bulb. What you saw is that none of the electrons are coming out. Got it? What you saw, that even I'm keeping on increasing the intensity but nothing is coming out. I keep on increasing the intensity but nothing comes out with the red light. Okay, but you use, I'll just use a different color so that it starts making a little bit more sense to you. So this is the red light, let's say. Okay, red light is incident, nothing is happening. Okay, you keep on increasing the intensity, nothing happens. And what happens? You use a blue light and you see electron coming out. And you have used a, let's say, a 5 watt bulb. Still you can see the photoelectric effect. Now when this photon is going to strike this electron, it's going to absorb the energy and it's going to come out. But these electrons are very specific. They won't just take any energy. They require energy greater than the threshold frequency. Alright, so this is how there is a frequency dependence on photoelectric effect. Okay, I hope Jay, I think now your confusion is clear. Yes, this is how you can think of the frequency dependence in case of photoelectric effect. So this turned the whole understanding upside down. We thought that energy of a wave depends on its intensity. Depends, if I put more and more and more and more watt of the bulb over there, what will happen is that I'm going to get electrons. That was not happening. So we cannot explain this phenomena by using the wave theory, because wave theory tells make it more intense and the electrons are going to come out. The energy is also going to increase. Over here the dependency was not on the intensity as it happens in case of all the waves. Rather it was dependent on frequency. And what Einstein told is that light consists of photons. These are the particles of light that we will call as photons, and each photon has got energy associated with it as h nu, where nu is the frequency. Okay, so so you're asking, sir, so would it be possible to explain it through the graph which is given? Okay, I don't know which graph you're talking about, but I can just tell you a graph if you want to know about it. So if you have if you need to draw a graph of intensity versus the photocurrent, once the photoelectric effect has started, what I'm saying is that once you start giving blue light, now you increase the intensity 10 watt, 100 watt. What will happen? More and more blue light. Blue light is capable enough to knock off the electron. So as you increase the intensity, what will happen? You will see an increase in the photocurrent. Because initially intensity means what? Like a 5 watt bulb is, let's say, giving 5 photons, and each photon is able to knock off 1 electron, which means I am getting 5 electrons in the circuit. Okay. Now 10 watt, it will be proportional, right? So 10 watt will give me 10 photons and it will knock off 10 electrons. So you can see that there is a direct proportionality. Got it? This is the graph I think you're talking about, right? But this only happens when the photoelectric effect has already started. Okay, got it? So yes, I was talking about some phenomena which you can explain it by wave nature, and certain phenomena which you can explain it by the particle nature. So reflection, wave nature and particle nature both. Refraction, you can explain it by both. Interference, only by wave nature. Diffraction, only by wave nature. Polarization, only by wave nature. And photoelectric effect, only by the particle nature. So that's the beauty of the photoelectric effect, that it actually refined our understanding of light. Now we know for sure that light exhibits a dual nature. Okay, it's wave as well as particle. So wave particle duality holds that light and matter exhibit properties of both waves and particle. Okay, yeah. So we'll just wind up our today's session at this juncture. I'll see you again in the next session with more interesting things, and again we'll continue solving some wonderful problems. So yes, we do have to accept this dual nature of light, because certain phenomena can be explained by considering light to be a wave, and certain phenomena you can consider light to be a particle. So well, with that said, this is your friend and mentor Mrinal signing off. I'll see you again. Keep learning.